Okay, welcome back to, this will be actually lecture 4.3. This is actually take 2. I recorded this earlier and it had no sound. So this is take 2 of lecture 4.3. So what we were talking about in lecture 4.2 was our PV indicator diagrams and how we had to know our equation of state to understand the processes, right? And we actually also talked about this very important idea of the quasi-static process, right? And how our equation of state was only valid along a process if it was done quasi-statically. But there was that important exception, okay? So now what we're going to do in 4.3 really is an isothermal compression. All right, so we're going to do an isothermal compression of an ideal gas. Okay, so this is going to be important because we're going to have the equation of state for an ideal gas. Remember what that is? It's PV equals nRT. Okay, so let's draw out our setup. Okay, so I'm going to do isothermal compression. So let's have a piston. It's going to be, of course, a frictionless piston. That's important. We talked about that before. This is my ideal gas inside. It has some pressure, volume, and temperature. And we're going to be able to apply a force down on our piston head. Now, this entire thing is going to be submerged in a bath. And that bath, along with the fact that we're going to have diathermal walls, means that heat is going to be able to flow in and out between our system and our surroundings. And here our surroundings are a fixed temperature bath, okay? And that's what's going to allow it to be isothermal. Okay, so we're going to fix the temperature during this process. Okay, so if we look back on our pressure PV diagram, our indicator diagram. So let's draw it up. Let's start at one volume, right? I'm call it V1. And that's going to be associated with the pressure P1. And we're going to compress to a state. So what we're going to do is we're going to push down on this, and we're going to allow the temperature to constantly equilibrate. And we're going to do it quasi-statically so we can follow our process along our equation of state. And the question is, where are we going to end up on our PV diagram? Okay. So the first thing to notice is let's write our pressure P equals nRT over V. But N and R and T are all constants, right? So this is like a constant over V. So now we know how to draw this for a particular temperature. It's like 1 over X, right? 1 over V. So we're going to have a nice curve like that. This will be V2 and P2, okay? So this is how we move from state 1 to state 2, right? We're going to move along that PV curve. Now, imagine that we're T1, one particular temperature. What would happen if we were to do an isotherm at a different temperature? Well, imagine we have the same initial volume. We would start at a higher pressure. We would again follow, I can do a slightly better job than that. we would still follow, well, that's not very good, our 1 over V to some other pressure. So this might be T2, and you might have another one where you get to T3, right? So in this scenario, T3 is greater than T2 is greater than T1. Okay, now, what about the work done in this process? What happens in the work? All right, so the work done, let me actually move that down here. PV, P equals nRT over V equals constant over V, and T3 is greater than T2 is greater than T1. Okay, so the question now I have is, what about the work done during the moving from state 1 to state 2? Okay, so let's redraw our PV diagram. So we have state 1, we have that nice 1 over x to state 2. We're going to move along this curve, and we're going to ask, what is the work in moving from state 1 to state 2? Okay. Well, we know from last time, it's minus the integral of P dV. But remember, the work is path dependent. It's really important to specify the path we're moving. So we're going to label the top and bottom of that integral as we're moving from 1 to 2. Well, we can see quite clearly that this is P dV. This is going to be the area under the curve. So the area under that curve is going to be the work done. So that's going to be work 1 to 2. Okay, now the question is, can we move the pressure outside the integral and get just the integral of P delta V? Just P delta V, I mean, by integrating that. And the answer is, of course not, because P depends on the volume, right? The pressure is different at each volume. So we actually need to know our relationship, but we've already done that. It's right here. Okay, so we're going to write minus the integral of nRT over V dV, moving from state 1 to state 2. Now we can take the nRT out, right? Because nRT, N and R are constant. We had a fixed volume, a fixed number of moles. The ideal gas constant is fixed. But also, we had a fixed temperature. This was isothermal. So now we just have to do the integral of 1 over V, which hopefully you know to be log V. But again, I'm going to show that this is integrated from V1 to V2. So that's just minus nRT log V2 over V1. Right? Log V2 minus log V1 is log V2 over V1. All right, now you can see here that I could also have written this in terms of the pressure, right? So I could have written this as minus nRT log P1 over P2, right? And it's flipped because these have an inverse relationship. Now, let's check the sign of this, right? So if V2 is less than V1, that means we're doing compression, right? So that means compression. And we said that whenever we're doing compression, we're doing work on our system, right? So hopefully we have a positive work under this integral. So if V2 is less than V1, log of a number less than 1 is negative. So I have two negatives, so I have a positive. And so that means the work from 1 to 2 is positive. If we had turned this around, and if V2 were less than, if V2 were, if V2 were greater than V1, right? If I went from here to here, right, and this were 1 and this were 2, will have done expansion, right? In that case, if V2 were greater than V1, I would have had done expansion, and the work from 1 to 2 would have been negative, right? So this was work on our system, and this was work by our system, okay? That's exactly what we said was our sign convention. So that's perfect. Okay, so that's lecture 4.3. I'm going to stop here, and I'm going to restart on 4.4 to do isobaric and isochoric compression. Back in a second.